So hi everybody. As you might remember, my name is Thomas Nacht. Thank you, Chris, for introducing me again. I've presented the Gnieving use case and will now present the WHY-Toolkit, for which I'm partially responsible together with some other partners from the consortium. So it's not only Forward Energy working on this toolkit, but it's actually large parts of the consortium working together. So I will present the WHY-Toolkit and also the results from our stakeholder consultation from our first phase of stakeholder involvement that we've conducted during the early phase of this project. So as Cruz already mentioned, the concept for the WHY-Toolkit is that we heavily rely on behavioral models when it comes to energy consumption. So we have our behavioral model built on the causal model and the causal diagram, which produces insights for us on investment decisions of individuals and also decisions on daily actions like for transport needs, is the car used or will public transport be used? All this information, this behavioral information will be fed into an energy service model, which basically transfers behavior into energy consumption. Um, for that purpose, we will create different mathematical and technical models of different appliances within the household or from a single appliance level, from washing machine, electric vehicles on the consumption side, but also storages and also generation capacities. Then to get to from a single household into a larger scale, we use the upscaling tool and then feed the data into energy system models. That way, we hope that the demand side of energy system models will be more representative and factor in behavioral aspects. So for that purpose, since the WHY-Toolkit obviously will be the best toolkit available out there for energy consumption of households, we thought, okay, even if we're very convinced that it will be the best toolkit out there, we still need to see what the potential users in the future and the stakeholders which use the results or the tools themselves think of the tool and what requirements they have. So our target was to identify the core requirements that this tool will have. So for that purpose, we've started the stakeholder involvement process where we've involved 14 policy modeling experts, 16 energy system modelers, and 33 end result users. End result users are policymakers, municipalities, industry partners like ESCOs, energy suppliers, or DSOs. And we have started 3 different types of actions: focus group, surveys, and interviews. And before I get to the results of the stakeholder consultation itself, one of the core results we have received from the whole process was we should have gone only for interviews, because the results received from the interviews were so much more in depth than from the other actions, which is mostly because in the interview you have the possibility to adapt to the corresponding stakeholders and then really get the answers you are grasping for, or even settle some uncertainties on the other side, on the stakeholder side. So basically, we have obtained a list of different key requirements, which are posted here. I won't read through them in step by step because I think you're well capable of reading through it yourself. But the most important things that we found out is something that we've heard already today about transparency, for instance, that our models and the results need to be transparent. We need to show where the data comes from, which assumptions were used, and how those assumptions and data relate to the results. That once we give somebody the results, they can say, okay, that's the framework in which the results were created. From a technology point of perspective, all of today's technologies and the main future trend should be in the models. This was something that we already initially thought of, but came as reassuring when the stakeholder also said that. From an intervention point of view, it was interesting to see that not only political interventions are interesting, but also business interventions should be considered, like new business models, new tariff systems, something that we didn't think of initially. And as for the results, a wide variety of expected formats for the results are there. So from raw data to really visualized data. And one thing that was very interesting for us is when it comes to the toolkit itself, it should be probably a standalone version rather than an online version, due to data protection issues when data is fed into the system, like consumption data or something like that. It should be rather on the system of whoever uses the tools themselves. So from that point on, we started creating the Y architecture. And the general approach is that we will first identify different energy behavior profiles. That is something that's currently going on, where we have load profiles and then analyze them to have them categorized into behavior profiles, and that then link that to socioeconomic profiles, which is the backbone of the whole causal diagram and causal model approach. And then we define an intervention for a scenario for a certain year. And for each of the energy behavior profiles we've defined previously, we then use the causal model to decide which energy investments will be made. So how the general structure of the residential building will change, and then we will simulate the whole behavior. We'll come to the simulation approach or the simulation architecture in the next slide. Then, as mentioned again, the results for one building will be upscaled to the larger scale, whatever the use case required. So for the Knieving use case, the upscaling process is not that big because Knieving is quite small. But if we go for the Europe use case, the upscaling process will be bigger, and the data will then be fed into the energy system models. So building on this general architecture, we developed a more detailed architecture for a WHY-Toolkit, which is shown on this slide. It consists of some main components. The first of all is the causal model, which will define the reaction of the residents of a building to interventions. So first off, some investment decisions, but also decisions on everyday life, like changing behavior. This causal model generates the data required to calculate or estimate the reaction of the building, or of the inhabitants in the building, which is separated into four distinct steps. So first of all are non-controllable renewable energies. So where we simulate the generation capacity of a building on a very granular basis, load profiles within at least 15-minute resolution. We have a load profile generator for the electrical system, one for the transport system, and one for the thermal system. And then we have where the electrical system obviously is the electrical consumption. The transport system provides information on transport behavior of people. And the thermal system provides the information on the thermal consumption of the building, which can then be met by electrical heat generation to satisfy the thermal demand. Here the system branches off. One side is the building sizing, which is used for investment decisions, optimizing the size of new investments, like a PV panel, if it's optimized towards own consumption or annual financial yield. And the household infrastructure simulation is where the flexibility of the model comes in, and where we go into the optimization sphere, where we then use flexibilities and optimize the load behavior of a household with the flexible loads to reference household optimization systems. And again, upscaling and in the use cases where the energy system models will be used. So we have different run modes for the WHY-Toolkit defined. We have the building sizing loop, which is actually basically used for calculating the effects of investment decisions. When I try to invest into a PV generator, a PV plant, solar panels, the question is how large is the roof, how high is my consumption rate, and do I want to go for maximum home consumption? If it's within the energy community setting, do I want to go for maximum generation? And this information will be fed into the building sizing algorithm, which will then decide, okay, according to the decision that an investment will be made, what will the effects be? Then we have the intervention optimizer loop, which will be used to optimize the parameters that an intervention has. For instance, a policymaker wants to create incentives to build additional PV plants. How high do these incentives need to be to get the maximum results? So we have here some loops where we calculate, okay, with different values or optimize that given the causal model, it provides us the information how people react to different incentives, how will that affect the whole energy system. And then in all shortness, the use case loop, where we calculate the different use cases and evaluate the questions that are asked there. And the counterfactual loop, which is basically the calculation of how the energy system would have changed if certain decisions would have been made in the past or would not have been made in the past. So we can create different business as usual scenarios here. So that's all in all shortness. Again, I've used up my time sufficiently and also a bit above it, but nevertheless, thank you for your attention, and I'm looking forward to questions later on.